So, hello everyone. I think we're now live again. So, welcome back to yet another edition of Quarantine Thermo. Today, we're very pleased to welcome André Timpanaro from UFABC. I already got permission from him not to try and butcher the full abbreviation in Portuguese because I won't be able to pronounce it. But we're very pleased to have him here today. He's going to tell us about some very exciting new work on Landauer's principle at zero temperature. So before I hand over to André, I will just do the thing that I always do, which is just kind of explain the format for any new viewers we may have. So André is going to speak, so I'll hand over to him in a moment and he'll speak uninterrupted for however long he likes. But we will have time for questions and answers at the end of the talk. So if you do have any questions during the talk or at the end, please just write them in the YouTube chat window, and please give your name while you write them if it's not already clear from your YouTube username. So with that said and done, I will hand over now to André. So please take it away. Thanks very much.
Thank you, Mark. Before I start, I would like to thank the organizers here for the wonderful work you're doing with this seminar series. It's been great so far. And as Mark has said, I'll be talking about this work here, Landauer's principle at zero temperature, where we show how one can extend Landauer's principle to the low temperature regime. Now, this work has been done in collaboration with these two gentlemen, Gabriel Landi, which many of you already know, and his postdoc, Jader Santos, both of which from Universidade de São Paulo. And this is how I'm going to be organizing this talk. Landauer's principle has shown up in some talks already in this series, but always en passant. So I think it's worth it to spend some time, go into a bit more detail, and start with an introduction to Landauer's principle. From there, I'll talk about some of the generalizations that exist of the principle already in the literature, and then we'll get to the core of our work. I'll talk about how these generalizations, in a sense, become trivial when we go to low temperature regimes, what is the source of this trivialization, and how one can get around it. Now, this will lead us to a new bound, and from there, I will do some comparisons between this new bound we arrive at and the usual Landauer bound, as well as showing some examples to see how this bound actually works in practice. Okay, so first things first, what is Landauer's principle? Being extremely superficial, Landauer's principle is the following. Suppose you have some system that is interacting with a thermal environment. Now, this interaction is going to cause a change in the entropy of the system and a change in the energy of the environment. In a nutshell, Landauer's principle is just a relation connecting these two changes. Now, if we want to get a bit more specific, we need to first put some assumptions into place. The first one is that we have an isolated system. And this isolated system has two different subsystems. One of them I'm going to simply call it the system S, and the other one I'm going to be calling the environment E. Now, note that environment here is just a label. There's no assumption about the environment being infinite. It can be whatever you want, as long as it is the subsystem of an isolated system. We'll make no assumption about the initial state of the system, but we'll make assumptions about the initial state of the environment and of the joint state of both subsystems. And particularly, we'll be assuming that the environment starts at a thermal state with temperature T, and that system and environment start out as completely uncorrelated. With that in place, we put them to interact, and we leave them interacting for a while, and this interaction is going to be causing a change, delta S of S, in the entropy of the system. Before moving on, just a note about notation using here. Delta S of S means entropy change for us. So the entropy, the von Neumann entropy, after the interaction, that is in the end of the process, minus the von Neumann entropy before the interaction at the beginning of the process. So final minus initial, which is actually the opposite of what is done in some papers in the literature of this principle. There will also be a change in the energy of the environment, and we can interpret this change as being heat flowing from the system to the environment, so we'll call it accordingly delta QE. Now, with all of this in place, Landauer's principle is this inequality here that is highlighted, relating the heat flowing from the system to the environment, the change in the entropy of the system, and the temperature at which the environment starts out. Now, this bound has been established some 6 decades ago in Landauer's seminal paper and has seen a lot of use. But it's almost always in a very specific scenario, which is when we have information erasure, which is the case where delta S of S is negative. Now, this subcase is very important because this implies that we can tell that delta QE is positive, and hence we know in which direction heat is flowing. Heat is flowing from the system to the environment, not the other way around. So this means that whenever we have a system and we reduce the entropy of the system, for example, when we erase some information that is stored in the system, there will be an inevitable heat exchange with some environment as long as the temperature is positive. And this caveat is the main point of our work. This can be taken to mean that information erasure has a dissipation cost, and this is very important because information erasure shows up in some very important situations. For example, if you have an irreversible computation paradigm, then you would be relying heavily in information erasure. For example, if you have a memory and you want to store new data in this memory, you first need to erase the old data that is in this memory. In this step, where you get rid of the old data, you are erasing information and hence you're dissipating heat to the environment. Another situation is when we are purifying the state of a system. This always reduces the von Neumann entropy and hence always entails some exchange of heat with some environment. Now, this connection between information erasure and dissipation cost has led to the claim that, although very interesting, I still think is a bit controversial, that information would be physical in a more solid sense than what's usually assumed, though I will not be entering in this more philosophical side of things in this talk. Okay, so now that we know what Landauer's principle is, why is it important? Why do we care about Landauer's principle? Now, this can be answered from 2 points of view. The first one that I'm going to be using is a theoretical point of view. Landauer's principle allows us, for example, to have a very satisfactory answer to the Maxwell-Demon paradox. Just to recap, the paradox goes like this. Suppose you have 2 chambers and you fill these chambers with, for example, a classical gas. And there's a passageway between these 2 chambers, and there is some device that can operate this passageway, opening and closing it without exerting work, that we'll call the demon. And the thought experiment goes like this. We put the gas inside the chamber, we leave the passage open until everything thermalizes, and from there the demon starts operating. And the demon operates in such a way that the passage is only open if a particle that is faster than average is moving from the right to the left chamber, or if a particle that is slower than average is moving from the left to the right chamber. Now, this is going to bias the kinetic energy of the particles in such a way that the left chamber is going to heat up and the right chamber is going to cool down. But once this happens, we can see that what the demon's actually doing is moving heat from the colder chamber to the hotter chamber without exerting any work, and so the demon would be violating the second law of thermodynamics, which is the paradox. Now, Bennett gave a solution to the Maxwell-Demon paradox in 1982 using Landauer's principle. And the argument goes like this. The whole idea is that the demon requires information in order for it to work. If I present no information at all about the microstate of the system, there is no way for the demon to operate in the way that I described. And since the daemon must operate the passageway, the daemon must be a physical device, and hence it must read the information from some physical medium. And this physical medium is what solves the paradox. There's essentially two ways we can transmit information to the daemon. We can either just present the information beforehand, or the daemon can obtain information by measuring. If we give the information beforehand to the daemon, we arrive back at the situation I described already, where we have a memory and we're trying to write data in this memory. We need to first erase the old data in the memory, and we must dissipate heat in this step. And this dissipated heat accounts for the change in entropy on the gas, so there's no violation of the second law. On the other hand, if the daemon works by making measurements, these can be either irreversible measurements or reversible measurements. If the measurements are irreversible, there is no paradox, the daemon's just dissipating during the measurements. But if the daemon works by reversible measurements, we arrive at Bennett's main argument, which is that even a daemon that uses reversible measurements requires to be set in an initial special state before each measurement. So we need to reset the daemon every time it does a measurement, and this reset erases information and hence dissipates heat. Once again, whenever we take into account all the dissipations, there is no violation of the second law. Another way that we can answer the question of why Landauer's principle is important is from a more pragmatic point of view, because Landauer's principle has a technological implication. And this implication happens because most of all computation that's done nowadays requires information erasure because it's based in an irreversible computational paradigm. And hence there will be a limit to how much information you can process by unit of volume and time, because we would like the integrated circuits we use not to fry during their operation. And this is true even for waveguides and circuit photonics that try to avoid Joule's effect. If you are still using irreversible computation, you have at least the dissipation coming from Landauer's principle. Now, in the current technological state, we're still far from reaching Landauer's limit. And from some estimates that I read, we're about 2-3 decades away from reaching the limit. But this is already starting to raise some concerns, and these concerns have been the major drive between the development of reversible computational schemes, where in principle you can do everything without information erasure, and hence you in principle don't need to dissipate heat. Okay, that's all I have for the information, for the introduction to the principle. And now I'd like to tackle this question: how we can generalize Landauer's principle? And first thing is what I mean by generalization in this case. What I mean by generalization is some new bound that works in the same scenario as the original Landauer bound, but that is stronger than Landauer bound in the sense that it implies the original Landauer principle. And when we're trying to generalize an inequality, and this has nothing to do with Landauer, actually, this is a more general principle. Whenever we generalize an inequality, there's two factors that must be taken into account. The first one is what information is being input into the bound, and the second one is whether or not the inequality can be saturated. That is, if there is some situation where equality holds, or if there is a situation where we can asymptotically approach equality. In the case of Landauer's principle, the only information that we're inputting besides the two quantities we want to relate with each other is the initial temperature of the environment. And we also know that Landauer's principle can be saturated if we do things adiabatically. For example, I can cite this paper by Yakshik and Pilet, where they study adiabatic switched interactions and show that this saturates Landauer's bound. So we are in a situation where we have an inequality that can be saturated. And there's only one way to really strengthen such an inequality, which is to add more information. So in the case of Landauer's principle, this means that any generalization in the sense of a strengthening of Landauer's principle must use more information about the setup besides just the temperature of the environment. Some examples of what is done in the literature: there are papers that use size information about environment, there are papers that use thermodynamic information about environment, or information about how the system and environment are interacting with each other. Further to example, this is a very non-comprehensive list of generalizations of Landauer's principle just for the sake of the argument. There's, for example, the work by Reeb and Wolf, where they view the generalization of Landauer's principle by assuming the environment has finite dimension. The extra information being input here is the dimensionality of the environment. There's also this paper by Good, Paternoster, and Modi from 2015, where they use information about how the system is interacting with the environment. There is this related work by Guarnieri, Campbell, Good, Pigeon, Vacchini, and Paternoster, where they use even more information about the interaction to get an even stronger bound. And I think you guys get what is the general line here. If you add more information, you get a stronger bound. There's actually a trade-off here. If you add more information, you need to obtain more information to use the bound, but you get a stronger result in the end. But something that is still kind of lacking in all of these generalizations, and this was pointed by Usdin and Rahav in their 2019 paper, which is still in the archive, but I think it's going to be published soon, is what they called the ultra-cold catastrophe, which is the fact that all of these generalizations so far become trivial in a sense when we go to very low temperatures. To understand what I mean by trivial, consider the following example. Suppose that you have here a qubit as your system, and you start this qubit in the maximally mixed state. And then you couple this qubit with an electromagnetic vacuum that's going to play the role of your environment. Now, if we let this whole system interact in time, then the entropy of the qubit is going to lower, because in case it was in an excited state, it would eventually emit a photon and decay, and hence the average energy of the environment is going to increase with time in a way proportional to the decrease in the entropy of the qubit. Oops. Now, if we ask Landauer's principle what it's happening here, it's going to tell us this, which is not very exciting, and in a sense is trivial, because we know that delta QE can't be negative, because this would entail reducing even further the energy of the environment, and the environment is already in the ground state. That's what zero temperature means. But this is only trivial with quotation marks, because the point here is that Landauer's principle is agnostic about the system and the environment. The only thing it knows is that the environment is at zero temperature. So the point here is that there is some system and there is some environment and some interaction such that we can make the same entropy change that a qubit underwent without exchanging any heat. But the point is that this process that saturates the bound is clearly not a simple relaxation. So it would be very, very useful to be able to go beyond this delta QE larger or equal than zero in situations like this, where we know a bit more about the system, we know a bit more about the environment. But the problem is that all of the generalizations here, they all give us this same prediction when we go to zero temperature. They all trivialize in the sense that they tell us the same thing the Landauer's principle tells us. So what we did in our work was that we went back to the original quantum derivation of Landauer's principle, which is spread out between these two papers from Esposito, Lindenberg, Van den Broek, and another one from Reeb and Wolf. We pinpoint where this trivial behavior is coming from, and we try to take a different approach that goes around the problem. Now, in the end, we're going to be obtaining a new bound that is stronger than Landauer's bound. And As such, it must use more information than the bound, and what we're actually going to be using are the equilibrium properties of the environment. And in fact, this all can be boiled down to the functional dependency of the heat capacity with the temperature. So just to show where the trivialization is coming from, I'm going to walk you through the quantum derivation of the principle, which is actually very, very simple. Okay, we start out by recalling what the assumptions behind Landauer's principle are. The first one is that we have an isolated system, so the joint state SE must be evolving according to a unitary. We start with the two subsystems S and E in an uncorrelated state, so the initial state must be a product, and the reduced state of the environment must start out as a thermal state with temperature T. Now with all of this, the changes delta S of S and delta Q of E can be written like these two equations here in the bottom. Delta S of S is just the change in von Neumann entropy between the reduced state of the system after and before the interaction, and delta QE is just the change in the average energy of the reduced state of the environment after and before the interaction. And the whole idea is to calculate these two quantities. This is actually a fairly simple exercise. Just calculate the relative entropy between the final and initial state of the environment and the mutual information between the system and environment after the interaction. We can rearrange these two equations to get this equality here in the bottom. And this equality here, if you know where to look at, is what's hiding the source of the trivialization at low temperatures. And the main point is that delta S of S is just a given quantity, basically. And the same thing can kind of be thought of about delta S of E. So both delta S of S and the mutual information are not going to diverge when we go to low temperatures. But this means that if we have any heat exchange at all, when we go to low temperatures, the terms here in red must be blowing up. And the source of trivialization is actually that all the generalizations so far, either directly or indirectly, are bounding the relative entropy by something that does not diverge when we go to low temperatures. For example, to recover the original Landauer bound, we just use that the mutual information and the relative entropy are always positive. And since we're bounding the relative entropy by 0 and 0 does not blow up when we go to low temperatures, then Landauer's bound is going to trivialize when we go to low temperatures. So the way we solved this problem is that we simply do not touch the relative entropy. We try as hard as we can to say absolutely nothing about the relative entropy. But we'll still be using the bound for the mutual information that it is positive. Now the way we found to do this is to consider the equilibrium entropy and energy of the environment that are given by these two functions here, and to define an auxiliary temperature beta prime that is the solution of this equation. Now since this thermal internal energy is always decreasing with beta, then this equation gives us a very well defined beta prime, so there's no question about what beta prime is. I'm going to give a more detailed interpretation of it soon. But the point here is that with all of this in place, we can express the heat exchange just using the internal energy, the original temperature, and this auxiliary temperature beta prime. The interpretation of what this auxiliary temperature is the following. Suppose you start with your environment in your thermal state with temperature beta. Then we put it to interact with the system. We go to a new reduced state, rho prime of E. Now suppose that the environment was infinite for the sake of argument. Then we could decouple the system and wait the environment to thermalize. And it would thermalize in a temperature beta prime. Now if the environment is not infinite, we can't thermalize, but the idea is that we just replace the state of the environment by the thermal state that has the same energy as the final state at the end of the interaction. And the point here is that we want to use the maximum entropy principle to tell us that the difference in entropy between this new thermal state and the original thermal state must be larger than the actual entropy difference caused by the interaction, which is the inequality here that is in blue together with its derivation. Now the idea is to add in both sides of the inequality the change in the system entropy. And when we do this, the mutual information shows up, and we use that the mutual information is positive to obtain this new bound here that is highlighted. And the point is that this is a generalization of Landauer's principle in disguise. To see why this is true, we did the following. We considered these two new functions, calligraphic U and calligraphic S, and we can basically sum up everything that we did so far in these two equalities here. Calligraphic U of beta prime is the heat exchange, and calligraphic S in beta prime is always larger than minus the change in entropy of the system. And this must be true no matter what beta prime ends up being. So we can just invert the first equation and substitute in the second inequality to obtain this new inequality. And this is already starting to look more like a generalization of Landauer's principle. There is the heat exchange in one side and the entropy change, but they are in the wrong sides. This is kind of answering the inverse question that Landauer's principle gives us. In the original Landauer principle, we give what is the entropy exchange and we bound the heat. Here we are given the heat and bounding the entropy exchange. Now to get to something that looks more like a generalization of Landauer's principle, there are some details here that need to be taken into account. If the environment does not support negative temperatures, then we can invert S and everything is beautiful. We obtain this new bound here that is very much what we would expect from the generalization of Landauer's principle. If on the other hand the environment supports negative temperatures, then we can still obtain this bound, but we need to take a bit more care. There will actually be two branches for the inverse of S, and we must always pick the one that gives us a positive solution. Okay, so this is now the new bound we arrive at. That is, the heat is bounded by this quantity, calligraphic U of inverse of calligraphic S of minus delta S of S. So now how does this compare with the usual Landauer principle? And it's actually much simpler than it seems at first to compare this with the original bound and heat that comes from Landauer. The whole idea is to create yet another auxiliary temperature beta bar that is given by this calligraphic S inverted of minus delta S of S. And the interpretation of this new temperature is the following. Suppose that you have your environment in the initial state at temperature beta, but now we increase the entropy of the environment by a quantity minus delta S of S, but always keeping the environment in a thermal state. At the end of the process, the environment would be in a temperature beta bar. But what's here really important here is that this beta bar is what's showing up in the argument of calligraphic U in our new bound. So the heat bound that we obtain is actually calligraphic U in beta bar. And if we apply calligraphic S in both sides of the definition of beta bar, then we obtain an expression for minus delta S of S. And we see that the Landauer bound is actually T times calligraphic S in beta bar. And to show that our bound is always larger than Landauer's bound, all we need to do is expand the definitions of calligraphic U and calligraphic S, move things around, and see that all that's happening here is a comparison between two free energies. And since these free energies are being evaluated at temperature T, then the state that minimizes it is the thermal state at temperature T. So the inequality here in the bottom is always true. And so if we go back in our implications, we see that our bound is always larger than Landauer's. Another way to compare our bound with Landauer's is to ask the question of when does it become similar with Landauer's bound. To answer that, we express calligraphic U and calligraphic S in terms of the heat capacity, to put everything just in terms of one function. And the bound is approached when our heat divided by T, which is beta calligraphic U, is similar to Landauer's bound divided by T, which is just calligraphic S in beta bar, which is the same as saying that the ratio between these two quantities is similar to 1. If we expand the ratio between these two quantities, we have these ratios between integrals, and the point here is that this thing here I highlighted in red can be thought of as just a function n of gamma that is normalized and strictly positive in this interval beta to beta bar. So it can be thought as some kind of weird probability distribution. So this is some kind of average of gamma over beta. So this is going to be 1 if and only if the two temperatures beta bar and beta are similar. And this actually gives us a bit more of insight of what our bound is actually saying. For example, it's going to be similar to Landauer's bound if that temperature change that I talked about when we raise the entropy of the environment by minus delta S of S is negligible. And this happens, for example, if the heat capacity is large. So for example, if we keep delta S of S constant, but we increase the size of the environment, then beta bar is going to tend to beta because the heat capacity is going to become larger, and hence our bound is going to tend to Landauer's bound. On the other hand, we can also scale delta S of S with the environment in such a way that we keep beta bar away from beta, meaning that the difference between the two bounds remains relevant even as both environment and system increases, meaning that this would also have some implications not just for very small environments, but also in macroscopic settings, as long as both the system and the environment are macroscopic. And what we're going to be seeing in the examples is that the particular scaling that we must use for delta S of S with the environment size depends heavily on what the environment is. This also allows us to give a different interpretation of what our bound means, which is not 100% rigorous. You can think of this as being a correction of Landauer's bound that takes into account the fact that we are heating up the environment. Since Landauer's bound depends on the environment temperature, if we start adding more heat to the environment is going to heat up, and we're going to be needing at each step more and more heat to keep causing the entropy change. This is not rigorous, of course, because we must assume also that the environment starts out in an equilibrium state and we are moving the environment away from the equilibrium. But I think this is, in some sense, a way of taking that into account. Okay, so now I'll move on to the final part and talk about some examples. First, a numerical one, which is the RABI model. And here we have an electromagnetic mode inside of a cavity, and this mode is interacting with a spin 1/2 particle. I'm going to be considering the particle as my system and the cavity as my environment. Now, the only thing that I need for my bound is what's happening with the environment. So the only part of the Hamiltonian that's relevant for us is the part in blue, which is the cavity Hamiltonian. We do statistical mechanics in this blue Hamiltonian and obtain the equilibrium energy and the equilibrium entropy. But now this equilibrium entropy is way too complicated, so can't find an analytical expression for the inverse of calligraphic S, but we can still do things numerically. We do this here for several different parameters of our model. We have here, more to the left, colder temperatures in the environment, to the right, hotter temperatures. Below we have a smaller coupling between the system and the environment, and in the top we have a stronger coupling between the system and the environment. Here in black we have the actual heat exchange between the system and the environment, In blue we have our generalized bound, and in red we have the Landauer bound. Now there's a lot happening here in these graphs. We can see, for example, in the graphs to the left that the Landauer bound trivializes to very low temperatures. It tells us nearly nothing about what's happening, but our bound remains there. It doesn't trivialize when we go to very low temperatures, so it doesn't suffer from the ultra cold catastrophe. We can also see that for weaker couplings, our bound gets very, very close to what's actually happening. And for hotter temperatures, this is also something that we see in nearly all the examples that we did, but we don't have an analytical explanation for that, which is that when we go to high temperatures, Landauer's principle seems to replicate our bound. So here in the top right graph, we can't tell the difference between the red and the blue curve, and while here in the bottom right we can just see some difference here right there at the peak, but the rest, the two curves are completely indistinguishable. Okay, so this is nice and all, but it doesn't give us a lot of insight because everything's numeric here. So now I'm going to do an analytical example, which is a system emitting to a waveguide, which is going to play the role of our environment. The only thing I'm going to be assuming about the waveguide is the dispersion relation and the length L that it has. We do statistical mechanics with these two informations, and we obtain the equilibrium internal energy and equilibrium entropy. From there we can obtain calligraphic U and calligraphic S. Note here that I'm using temperature instead of inverse temperature. It makes no difference at all, really. And this calligraphic S is simple enough that I can invert it and substitute it inside of U to obtain an analytical bound for the dissipated heat. And we obtain this formula here in the middle, where we see that we have first the Landauer term plus a strictly positive correction. Now this correction is remarkable because it first remains positive always, so it reflects the fact that we have a stronger bound than Landauer's principle. It does not depend on the temperature, so it clearly does not suffer from the ultra-cold catastrophe, and it has size dependency that reflects what I said earlier about the heat capacity. As the heat capacity increases, which happens as the waveguide becomes longer, our bound approaches Landauer's bound. Now I'm going to make a very fast back-of-the-envelope calculation here of when the correction it has a larger magnitude of the compared to the usual Landauer principle bound, which is essentially this inequality here. We can rearrange things to have in the right-hand side the information change measured in points, and on the right-hand side we have basically a constant times temperature times length. And this is very interesting because you see that the temperature and the length are playing the same role essentially on telling when the effect is dominant, which ties in a bit with what we see in the RABI model, that not only as we increase the heat capacity, the two bounds tend one to the other, as we increase the temperature, the two bounds will tend to each other. Now this inequality is satisfied in the blue region here in this graph, and what's really interesting here, I think, is the scale of the things. The length of the waveguide needs to be in the tenths of micrometer, and the temperature must be in the range between 50 and 100 Kelvin. So this seems to be very easily accessible for an experiment. So I think a carefully constructed experiment should be able to see without much problem this effect. Now just to close the presentation, I said that the scaling that we must use in delta S of S depends heavily on the environment, and essentially this depends on how the heat capacity scales with the temperature for low temperatures. This is a comparison between three different types of environment. The first one is the waveguide we already studied, that scales for low temperatures as T. the heat capacity, and the dissipated heat is going to be scaling as delta S of S squared divided by A. A is just an extensive parameter. In the case of the waveguide, is the length. If you have phonons in 3 dimensions, the heat capacity at low temperatures scale as the third power of T, and the heat is going to be scaling like delta S of S to the fourth to the third divided by the cube root of A. And another interesting case is when we have a gapped environment, for example, a BCS superconductor. The heat capacity scales exponentially, and the dissipated heat scales essentially as delta S of S over log of A, which in this case is also the volume. So if we want to keep our bound relevant, in the case of the waveguide, we must take delta S of S to be about the square root of the size. For the case of the phonons, it must be the fourth root of the size, and in the case of a gapped environment, it must be on the order of the logarithm of the size. So you can see that the scaling changes wildly, depending on what the environment is. Okay, that concludes everything. The takeaway message here is that we can generalize Landauer's bound to the low temperature regime. We can beat the ultra cold catastrophe. We don't need information about the system for that. All we use is information about the environment, in particular the heat capacity. And this is interesting because the heat capacity can be obtained either by modeling or by experiments, although I think it's more feasible to obtain them from experiments in a classical setting than in a quantum setting. Correct me if I'm wrong. And these deviations, this extra heat that we must have when we compare with low Landauer's bound, depend not only on the environment size, but also on the size of the exchanges. So we can actually adjust things in such a way that the new bound remains relevant even in a macroscopic setting. That is, even if we go to the classical limit. Okay, that's everything. I'd like to thank everyone organizing this series once again, and everyone that came here to see me talking today.
Thanks very much, Andre. Really interesting and very clear. So yeah, we have plenty of time for questions. So as I said before, if you have any questions, feel free to just write them in the chat window. We already have several questions, so let me go through them. I also have a few questions, but let me start with the ones from the audience. So there were a couple of questions from Junjae Liu. The first one was asked near the beginning of the talk. I think you actually kind of half addressed this point, but I'll go ahead and ask the question anyway, because it's always good to have repetition. So Junjae Liu says, can this dissipated heat increase the temperature of the environment initially at T equals 0, or do we just neglect this effect by assuming an ideal bath with infinite degrees of freedom? I guess this effect will be relevant for a finite bath. Is this right?
Actually, if we go to an infinite bath, then you need to be careful and how you take the limit. For example, this bound is still going to be relevant if you have an infinite system interacting with an infinite bath. I think one interesting way of thinking about this is that we have this is basically a bound when we have two systems interacting with each other. One of them is in a thermal state initially. It doesn't matter if they are macroscopic or if they are microscopic. As I said when I was talking about heat capacity, if the environment is way too large compared to the system, the change in the entropy that you can cause in the system is way too small, and you essentially recover Landauer's principle. And what you said about the environment heating up is also what I think is actually the correct interpretation of what this new bound means. This is the correction due to the heating up of the environment. If the environment does not heat up, then you essentially have beta bar equals to beta, and hence this bound is essentially the original Landauer principle bound. Okay,
so maybe I'll just skip ahead to the next question by Junjae, because this is directly relevant to what you just said. So the question was, what's the origin of the temperature independent correction to the dissipated heat? So you've just given one explanation, but the question was, can I understand this as a kind of 0 point fluctuation like correction? I mean, do you think this makes sense, or?
You mean about the? I'm not sure if he's talking about this one here in particular, because this is an example that I cherry picked because it's one example where the bound is particularly nice.
Right.
And because for example, you can make the same bound for. You can actually find the analytical expression for a system that is emitting to. For example, the example I gave right at the beginning of spontaneous emission to an electromagnetic vacuum, or you can assume that your electromagnetic field is not in a vacuum but is contained in a box. You have a correction, but it's way ugly. It still can be thought as minus 2 delta S of S plus something that is that goes to 0 as the exchange goes to 0. The one thing is that the correction is not always temperature independent. That is the first thing. This is actually something that is particular of the waveguide example.
I see.
What I actually think is the correct interpretation is that once you start kicking off the entropy change, you add a bit of an energy to the environment. The environment is no longer at 0 temperature, and then you will have to add a finite amount of energy to get the next kick in the entropy exchange, and this starts building up. Mm-hmm. In fact, this doesn't really have anything essentially quantum behind it, because of the arguments that are really used are based on the maximum entropy principle. This should be still derivable, I think, in a purely classical set. So I don't think there's anything to do with fluctuation, 0-point fluctuations here.
Okay, thanks very much. It's very interesting. Okay, so we have lots of people saying thanks for a lovely talk and clapping. Mm-hmm. The next question, I think, which I just skipped, was from Nadia Bernades, who asked, do you do the numerical calculation for the RABI model using quantum trajectories?
I would need to ask Jader because he was the one that actually made those simulations.
Okay.
But I think he was actually calculating the evolution of the density matrix, actually, because the system is simple enough. Then you can just evolve Rho here. This is a very low dimensional system here.
Right, at low enough temperature anyway, so you don't have to worry about the bosonic.
So I think he was taking just he was like putting a cutoff about what is the maximum energy of the mode here, and then just doing a finite dimensional evolution. Mm-hmm. I think that's what he did. Yeah. I would really need to ask him.
Okay. All right, so I think we had the next question was from Devira Segal, who asks, seems like you are not making any assumptions on the dynamics, right? Can it be non-Markovian?
Yeah, in a sense, this, and I'm not sure if this can be thought as a consequence of non-Markovianity, but it's interesting the fact that it is only relevant when the environment, for example, if you have a small system, it's only relevant if you have a small environment. And if you have a small environment interacting with a small system, there will be backflow of information. Mm. So, if you're not in the macroscopic case, there will be non-Markovianity here. I'm not sure if this is a signature of non-Markovianity, if it's a consequence of non-Markovianity, but it holds exactly in the same regime where you would have non-Markovianity.
Mm-hmm. Okay, maybe I can ask, actually, I had a follow-up question. Well, I had a question which is a perfect follow-up to this. So I was interested in this waveguide example as well, because, I mean, if you have a finite length waveguide, I mean, eventually the excitation that's emitted into the waveguide could reflect off the end and come back, right? Yes. So are you assuming here, when you say delta Q, you're assuming that you're looking before this reflection comes all the way back to the system? Is that correct, or?
Not at all. In fact, if we go here to the Landauer principle for the RABI model here, you can see that you have those oscillations here. This is exactly backflow. You have the excitation moving from the system to the environment, back to the system, back to the environment.
I
And you
see.
can see that it holds always.
Yeah.
So the point is you have some unitary evolution. The point is that ideally you would leave it to interact by some time, and you would stop and use the measurements at that point at which you stopped. But what is here in this graph, for example, is what would happen if you would stop at here or here. Or I remember you can see my cursor.
Yeah.
If you stopped at different time steps, what would you see if you stopped interaction at that point? So yes, you can have the excitation coming back. There's no problem at all.
Okay, that's really cool. Thanks. All right, so the next question was from Essen Nazir, who says, can you generalize the correlated initial system environment states?
What would change? Yeah, if you assume the environment starts in a thermal state, I think you could do something. Because if you go here back to the derivation, what would happen is that you would have an extra term here in the mutual information. And this basically harks back to this equality here. You have a correction here in the mutual information, I think. And from there, what you would need would be, yeah, I think the extra information you would need is what the mutual information is between the environment and the system, and then I think this would end up being an extra term in beta delta QE. I think, yeah, I really need to think about how because you need to redo the calculations, but that should be possible. Yes.
Okay, thanks very much.
I'm not sure if it's as clean as the derivation we did, but I don't see a very strong argument of why it shouldn't be possible as long as the environment is still thermal.
Okay, cool. Great. So thank you for that. Then I think, okay, we had another question from Dvera, who said, interesting point about non-Markovianity. By the way, why not study the simpler model of coupled harmonic oscillators, which is simpler than the RABI model?
There was really no need for studying the RABI model at all. Yes, it's just we picked one.
You just like it. Yeah.
There's no deeper reason why we picked the RABI model. It just seemed like a cool example.
Cool. Okay, fair enough. All right, so then John Gould has a question. Can you connect your result to Steinspring dilations for channels that perform erasure? If I think of some non-unital channel, can you think about the energy change of an ancilla in some higher Hilbert space?
Yeah, I would need to think a bit more about that before answering. I'm not sure.
Okay.
That's a very good question.
Okay, maybe that's one for you guys to discuss some other time. Okay, so okay. I mean, let's see. So if anyone has any more questions, feel free to write them in the chat window. Maybe I will ask one more question, because I mean, when I read your paper, I was really interested in this example about the gapped system. You know, you have this example where if you have a BCS superconductor with a gap, then basically you get some analytical result for the kind of new Landau bound. Do you have any intuition for what this means, this bound? You showed it in your last slide, I think, this logarithmic scaling.
What I think is happening here would be what this means here essentially is that it's very in a sense it's if you want to for example, let's think about, for example, information erasure. Suppose that you want to erase some information using a superconductor as your environment. What this is telling you is essentially that the correction is going to be, at least if you compare with what would be for a waveguide and a phone, it's going to be very large, the heat that you're going to be needing, even for a small information erasure. So I think this would be mean that you would need to at least raise your environment from the ground state to at least the first excited state, but there's a gap between two in the superconductor. So you need to do you have a lot of things to push, let's say, to move from the ground state to the environment, and this ends up causing this change in the dissipated heat for low temperatures. Once you're beyond low temperatures, this is not such a problem. And this was an example that we picked more because of this thing that it could be in a situation where your system is very small and your environment is very large, but still you would be seeing a visible effect because of this difficulty of moving from the ground to the first excited state. That was the intuition that we had when we thought of doing this example.
Yeah, that makes sense. Sorry, go ahead.
From an analytical point of view, it's due because of what's happening here with the heat capacity when you have very, very low temperature, which is the fact that it's non-analytical. All the derivatives are zero. So you start heating up the environment before you actually change the energy in a non-negligible way. So you just do a very little kick and then you're back to the positive temperature case, essentially.
Okay, great. Thanks very much. That's really interesting, and that makes a lot of sense. Yeah. So I think that's it for the questions. I think I got all of them. Hopefully, if anyone has any further questions, I think of course you can email André. I'm sure he'd be happy to answer your questions about the work. So let's conclude it there. So thanks everyone for tuning in once again, and especially thank you very much to Professor André Timpanaro for such a really interesting talk. Thanks.